Bismillah ar-Rahman rahim. So let's start with the today lecture, and this is lecture is much important because we are starting with the Schrödinger wave equation, and this equation we will be using in the coming lectures to define the translation movement of the electrons, its vibration movement or the rotational movement. So this is very important here, and here we will do some basic mathematics. So I will explain along with the derivation where there is the use of the mathematics to understand the basic concepts about the Schrödinger wave equation. So actually this equation is the linear partial differential equation because we are going to use the differential partial differential to derive this equation. That's why this is called the partial differential equation. And what is this? We will be explaining during the lecture that describe the wave function or the state function of a quantum mechanical system. So this particularly is going to define actually what is the wave function. This is all about the wave function and its properties, and then the what are the other parameters which are there. We are going to look into detail. So this is the Schrodinger wave equation. This is the final form. Actually, I am going to show over here to just have a look. What are these parameters? We will derive this half of the portion. We will derive this in today's lecture, and then the rest we will discuss in the next lecture. So what are the different parameters are over here, and this is called the second derivative with respect to the x. X is the position of the electron. So d square over dx square is the second derivative, and actually this is the one form of the partial differential, and that's why this equation is called the partial differential equation. And this is the sign is the psi, and here this is called the Schrödinger wave function or stationary state wave function, as we have discussed in one of the lecture about the stationary wave function and the other moving wave function. And this is actually the important over here. We want to further discuss what is the wave function according to the Schrödinger wave equation. And this x is the position of the electron. This E is the total energy, and V is the potential energy, and this is the here, and here this is the actually the mass of the electron. This is the Planck constant. This is the pi, which is the constant. It is the constant, and then let's have a look. What is the E over here? Here is the total energy, and total energy is the sum of the potential energy, and T over here is the kinetic energy. So total energy is the sum of the potential energy and the kinetic energy, and this is another form of the this equation. So don't worry about this one. What I am going to show over here, just have a look. Actually, these are understanding of the symbols are important because we will be discussing in the rest of the lecture, and these equation we are going to derive. So don't be worried at this stage how we are going to do with these equations. So, and this equation is just the rearrangement of this equation. If you have a look over this, and this is all equation equal to 1, and just I am just moving this factor to the right hand side, and this equation will become this, and there is no difference between these two equations. And here actually this is the whole factor is called the kinetic energy operator, and this is the total kinetic energy. So this total energy is the with the describing the wave function, potential energy describing the wave function, and this is factor is the kinetic energy, total kinetic energy, or the kinetic energy we call the operator, kinetic energy operator. and this is the total kinetic energy. So actually this is one of the postulates of the quantum mechanics, and I will discuss the four basic postulates of the quantum mechanics at the end of the course, because I will be discussing all of these things during the course. And what are these operator? And here you have a look, this is the kinetic energy operator. And for the simplicity in quantum mechanics, instead to write this one, we say this is the kinetic energy operator, just to replace this whole factor with the T, or T with the this long factor, which is called the kinetic energy operator. So this equation does not contain time. Here you have a, if you look at this equation, it is not mentioning over here the time. That's why this is called the time independent Schrödinger wave equations. So I'm just going to replace this equation into another form, because in different books and notes which are provided to you are showing different form of the equations. So these equations are similar, so there is no difference, just there is the change due to the replacement of one symbol with the other one. So let's suppose this is actually the new one, maybe you know, this is the reduced Planck's constant, and we call it the h bar, and here the bar is indicated over here, and this equal to h over 2 pi, and h, you know, this is the Planck's constant, and here, you know, this is the Planck's constant, this is the pi. So I am just going to replace this one with the reduced Planck constant, just to make this equation more simpler as compared to this one, which is looking too much complex. So by taking the square of this one, this is the h bar square will be equal to h square 4 pi square, because this will be 4 pi square. And now I am just replacing this factor with this one, h square 4 into 2 pi square, and this I'm going to replace with the h bar, and this equation will become like this. So I'm just replacing this whole factor by considering this one into this equation, and what is left, 2 and m is left, and rest you can replace with this the h bar square. Other, there is no change, this is the same thing, potential energy, and this is the total kinetic energy. So the main important part to consider over here is the all these three equations are the same, and now we are going to derive this equation in the coming lecture. So first, now the electron, this is the angular movement of the electron in a shell. So this is the center part. Let's suppose this is the P is the particle, and it is considered as the harmonic motion, and this is the harmonic motion, and this is the harmonic wave. And what is the harmonic motion? As we have already discussed, but it is the repetitive movement back and forth through an equilibrium or the center position. So let's suppose this is the center point, this will be moving this side or this side, and or like a pendulum, if you just to move over here, then it will be moving back and forth with the same distance through the equilibrium, through an equilibrium of the central point. So this electron will be moving in a harmonic motion, and of course, according to the our previous lecture, according to the de Broglie equation, when this red is showing, let's suppose this is the harmonic motion of the electron, when it is moving in a circular motion with some angular velocity, and it must be uh, creating a wave, and because the particle-like properties of the wave and wave-like properties of the particle, and here it is the wave-like wave-like properties of the particle, because we are considering electron as a particle when it is moving in the circular path, and this is going to display wave-like properties, and this I have shown over here. So let's have a again to look on these three different points, and this is the actually the central point. let's suppose this is the p is the particle, and particle is moving at the o position, or the zero position, and it is moving in this direction, and it is covering some path moving this and this, and at the end it is again reaching this point. And when it is moving to this path, this is covering the one fourth of the circle, and this is actually from here to here, this is the one fourth of the circle. This is the half wave, and this is another half wave. That means this is the full wave over here. And this, if it is moving into this direction, and this path is covered in a circular path, and what is creating over here, this wave is going to be displayed over here from 0 to this. And if it is moving like this into this at this point, then the wave should be at this. And similar, this behavior is going around the circle. So here, this is the wave function. Actually, if you have a look, this is the central point, and how much distance this is going to cover from the central point. This is the radius, and this is shown over here. It is the a, and the position from 0 to p. This is the actually as shown over here. This is the wave function, and this is the wave function you display in a circular motion, and this is display in a wave. So I am going to further clarify this concept. This is much important. Maybe after the lecture, you can discuss with me more. But listen carefully, because it is very important to understand what is happening with the particle moving in a circular path and creating a wave alongside. And this is the wave-like properties of the particle. Again, and this is the safe movement as I have explained before. And just to clarify the concept, I have shown over here the two again pictures, and this is the circular movement of the particle in a shell. Starting, this is a central point starting from this at the 0 point, and then it is moving into the circular path. And here, to understand it, what is actually, how much distance is going to be covered. If you look at the this is the circular movement, this is the total circumference of the this circle. And you may remember, this is the 2 pi r circumference of the this circle. And it is divided into four parts. It is half, and this is further you can half. It is four parts: one quarter, second, third, and the fourth quarter, and it is displayed over here. So let's start with the first one. The electron is moving from this point, traveling to this side, and it is going to, from here, this is going to, maybe you can start here, but it is better, I would be considering this 0 over here to start with the wave. And wave is like this is covering this part, one quarter which is covered over here. This is the one quarter, this is one quarter. And if I ask you how much is the angle from the starting point, it is covered over here, or it has formed in the circular movement, and this is the 90 degree. If you have this and this is the actually the theta over here, it is the 90 degree. And this theta we are talking about, actually we will use this one to derive this equation. And then when the electron is moving to the second half, and this is the total circumference is the 2 pi r. That means 2 pi is important, and here r is, let's suppose, is a constant, it is 1, and 2 pi is important. So that means this whole circle I am going to divide into the four parts, and then each circle will be the pi over 2. So this is the pi over 2 covering how much angle it is going to form. It is 90 degree. Within 90 degree, the it has covered the distance, which is the x position, how much distance is going to cover. This is the pi over 2. And in the second half, half pi plus half pi, it will be the pi. So that means and how much angle this electron has covered from starting from here to this point. This is the 180. So 180, the distance is traveled in a circular path is the pi, and then it is moving to the third quarter. Again, it will be 3 pi over 2. It is just the half pi over 2, sorry, this is the pi over 2 plus pi over 2 plus pi over 2. That means this is the 3 pi over 2 or 3 by 2 pi. That is a similar thing. And how much angle it has covered from starting point. This is the 90, 90 and 90, and this is called the 270. And similarly, when it reaches to the fourth quarter, this is the fourth of the pi over 2, 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 and this will be actually 4 pi over 2, or you can, it is the 2 pi, and this is the circumference, that is the 2 pi. So it is traveling from this point and reaching again to this point. How much distance it has traveled, this is the 2 pi, and how much angle it has traveled, this is the 360. So whenever the electron is moving in a circular path, it covers maximum angle 360 with the distance travel is 2 pi. So this is a very, very important explanation over here, and you must remember this one in the future lectures. I am going to use these explanation to drive the Schrodinger wave equation. And now, what is this, the theta? And theta you may call, this may be the sine theta, cos theta, or the tan theta. So all explanation over given over here, maybe I will explain in the next slide for more about the sine, cos, or the tan theta, and which one we are going to use to drive the Schrodinger wave equation. Now, this is the same circular movement which I have explained, and here the theta we are going to be used as a radians, and this one theta, so the theta is the 1 radian. How can you explain? And 1 radian is the measure of the central angle whose arc length is same as the radius of the circles. So what does it mean? This is the radius of the circle, and when this circle distance equal to, this is the arc, and when this length is having the same distance as shown over here, the distance traveled in a circular path, so this is called the arc, and then this is called the, at this point, this is called the radian, 1 radian. This is called the 1 radian, and this is explained over here. And 1 radian is 180 over the pi, as we have explained earlier. Half this quarter is the half pi, and how much distance, half pi plus half pi, this is actually the pi, and how much distance it has traveled from this to this point, how much angle is the 180. 90 plus 90, this is the 180, and this is called the 1 radian. So we will be using this in the Schrodinger wave equation. So now consider this triangle, and you may actually uh, draw a triangle on any part, but just for the simplicity, I'm going to show over here in the first of the quarter. This is the triangle P, B, and C. And what is important over here, this theta is important, and this may be the sine theta, cos theta, or the tan theta. What does it mean, the sine theta? This opposite was oblique hypotenuse. The angle, this is the opposite to, this is the theta, and this side is the opposite, and this is the hypotenuse, and then the ratio between this and this is called the sine theta. And what is the cos theta? This is the adjacent, and this is the hypotenuse, and the ratio between these two is called the cos theta. And for the tan theta, it is the opposite divided by the adjacent, and ratio between those two is called the tan theta. and here we are going to use the sine theta. So sine theta will be as explained. This is the theta. This is the opposite divided by the hypotenuse. Opposite is the A, and divided by the hypotenuse is the C. So A over C is called the sine theta. And here uh, by using this equation, this triangle, this is the PC. PC is the opposite, and what is the PB is the hypotenuse. So PC divided by PB is the sine theta, and here PC is the actually the distance between PC will be equal to this wave function, and PB will be equal to A. A is the, here it is the radius, and again we will be solving this more in the translation movement of the particle when we further go with the Schrodinger wave equation. So this triangle, actually this is important, sine theta will be equal to PC over BB as per trigonometry function, and this PC will be wave function divided by the A as it is indicated over here. So here, as explained before, this is the wave function, and it is the Greek letter which is called the psi. And now moving to the, because this electron is moving in angular movement, and actually this is the angular velocity. W is the angular velocity, and what is the angular velocity? This is the theta. It is going to form in radians per second. So actually velocity is the distance covered per second in a direction. So here direction is the angular movement in a circular path. So angular velocity will be theta over t. T is the second, and this radians is the theta, what angle it is going to form by moving from 0 point to any of the position, as I have explained before. So actually theta is important. This is going to change. This is 90, second quarter is the 180, then 270 and 380. So this is, it will remain, maximum is the 380, and this is called the angular velocity, and angular velocity over here is the theta divided by t. T is the second and theta is the angle as explained over here. This is the sine theta. So if you want to calculate the theta, theta will be equal to, you can multiply the t with the angular velocity, it will become, theta will be equal to angular velocity multiplied by t. And now put the value of this theta in the equation. Equation is over here. So when you, this is the first is just the arrangement. Now what there are two rearrangements. So psi over a will be equal to sine theta, and if you want to get the psi, so a will be going to multiply with sine theta. So sine psi will be equal to a sine theta, just rearrangement of this equation. And now using this equation you can put the value of the theta, and theta is wt in this equation, and this equation will become a sine wt. So psi will be equal to a sine wt. Now again w will be theta over t, as we have explained before. So it is going to be end within 10 minutes, so maybe you can join again if it is going to be stopped during the lecture. So just I am going to wind up this equation. So as we have explained earlier, W angular velocity will be equal to theta over t, and the t will be equal to theta over w. Just rearrangement of this equation, and this theta, the maximum value or the theta will be equal to 2 pi, as this is the same I have explained before, because in the circular path, this the maximum angle when it's covered 360, then the theta will be equal to 2 pi. So because there are the 4 quarters, 4 half pi will be equal to 2 pi. Or there is another explanation, you may consider this one. because the circumference is 2 pi r and the r is the radius and which is considered 1 for any unknown frequency. So the rest will be 2 pi. So you can use this explanation as well as I have explained before. For one full cycle of the sine or cos wave is 360, so which is equal to 2 pi radians. So theta will be equal to 2 pi. And when you put this value over the above equation, this theta, just to replace or put the value in this equation, now the time will be equal to 2 pi over omega, that is the angular velocity. And here the time is important. If you recall our first lectures or the second lecture in this course, maybe you can watch again the video at the start of the lectures. So we have explained in detail what is actually the frequency, and this is frequency is the cycles per second, and how much cycles the wave has completed in unit second, that is called the frequency. And actually this frequency, if you can say, this is the 1 over t, because these are the, this is just elaborating the cycle, this is the cycles, one cycle completed in a unit second, and this is called the frequency. And maybe you can reverse this one, t will be equal to 1 over mu is the frequency. So now I am just replacing, putting the value of t in this equation. So this is the frequency is 1 over t, and now this equation will become, just putting the value of t over here because this is the double reverse and this is moving upward, and the equation will become omega over 2 pi. Or you can say the omega will be equal to 2 pi mu. You can multiply this with the frequency. So now we have actually derived what is the angular velocity. This is the w, omega will be equal to 2 pi mu, and this is called the angular velocity. Now put the value in the below equation, and this is the same equation we have discussed in the previous slide. So psi will be equal to a sine wt. Now I'm just putting the value of this omega in this equation, and this equation will become psi will be equal to a sine 2 pi, this is mu, and t, just replacing this in case of the angular velocity omega. Now further moving, actually now I'm going to replace the, actually this is the time independent equation. I'm just replacing the time by using the other factor, and for the wave distance variation, that means distance time relationship, and the speed will be the x over t. And you know speed, the distance traveled in unit time, that is called the speed. And if you want to calculate the x, so x will be vt. So here it is displayed over here, x equal to vt, where x is the distance covered in time t at speed v. So these are the just very basic things. You must always remember what is the speed, what is the velocity, angular velocity, or what the other factors we have discussed in other case of the Schrodinger wave equation. So what is the important over here? I am just want to replacing this equation. So t will be x over vt, just the rearrangement of the previous equation. Now putting the value in the equation. This is the same equation. I am just repeating again and again because it is difficult to move to the previous slide. So this we have already derived in the previous slide. Psi will be equal to a sine 2 pi mu t. And now put the value of this t, and t is x over v in this equation. And this equation, just replacing the t with this, will be x over v. So this equation is the just the starting of the or we have achieved to the one part of the derivation of the Schrodinger wave equation. So I am going to keep this derivation at this point, and then in the next lecture we will be further moving to the rest of the derivation. So we will achieve the final version of the Schrodinger wave equation as explained in the previous lecture. So here I am just going to this